Welcome everyone to this presentation called A Simpler Alternative, Minimizing Transition Systems Modulo Alternating Simulation Equivalence. I'm Gabriel Gleizer. This is a joint work with Khushraj, Madnani, and Manuel Mazo at TU Delft. A popular approach for control synthesis of hybrid systems or systems with difficult complex specifications is by using abstractions, meaning we convert the original control systems that are infinite state into finite state systems where we have algorithms that can solve a control problem in finite time. Control specification is typically given in terms of a temporal logic. And it's a very simple example. We can have an electric kettle that we want the temperature to eventually reach the range between 90 and 95 degrees Celsius, and then always stay in this range. We can abstract this problem if you measure the temperature continuously, but the control action is either switching on and off the boiler using this finite automaton, this finite system, which has state set, an initial state set, an input set, an edge or transition set, an output set, and an output map. So these are the four states representing different parts of this original state space, where we label each of them with their different output, cold, good, or hot, and we place transitions depending on whether the boiler is turned off or on. And in this system here, we can easily find a controller that satisfies the specification. Now, typically, these systems are much larger than this very simple example. And therefore, even though we get a finite system, it may be impossible to finalize the computation of the controller in finite time. So we address the problem statement of minimizing a finite state control system. What does it mean by that? Is that given a finite system S, we want to find an equivalence system S prime, such that for any possible LTL specification, a controller exists for S if and only if a controller exists for S prime. And controller for S prime can be used, or we call refined on S. But moreover, we want to minimize. We want the S prime is the smallest possible system that satisfies all of this. Now, the conditions 1 and 2 are attained if S prime is a so-called alternating simulation equivalence system to S. And we define the size of a system by the triplet composed of the size of the state set, of the transition set, and of the initial state set. We prove that we actually construct a polynomial algorithm on order of the transition size squared to obtain this minimal system S prime, and we show that there is a unique system that is minimal S prime that is subject up to a special type of isomorphism that I'm going to explain later, BABI. Now, what is alternating simulation? This is a bit of a cumbersome notation to digest. We say that a system SB is an alternating simulation to a system SA, denoted by SA smaller or equal than SB, if there exists a relation on the states satisfying these three conditions. Now, I'm not going to go through the definition because there's a lot of alternation of quantifiers. If there's a relation, we say that there is this R is an alternating simulation relation from SA to SB. The intuition behind it is that if XA, XB belongs to any relation, then the environment is more powerful on XA, or at least as powerful on XA than XB, whereas the controller is more powerful on XB than in XA. So they have the same output, but it's easier for the controller to move forward, attaining whatever specification it wants if it's on XB than XA. While in XA, it might be that the environment has more transitions to counterplay the controller. So SA is harder to control than SB, or at least as hard to control as SB. We call alternating simulation equivalence when SA is smaller or equal than SB, and SB is smaller or equal than SA. This is the notation we use. While bisimulation is stronger in that we need a relation that is an ASR from SA to SB, while R minus 1, our inverse, is an ASR from SB to SA. It's clearly stricter because in the former, in the equivalence case, we can have different relations here and here that are not necessarily the inverse of each other. Therefore, we have more degrees of freedom to minimize the system if we use the equivalence rather than bisimulation. What is our algorithm? We take a system S and we do a pre-processing, and then we apply 4 steps. Step 0, the pre-processing, is to compute the maximal alternating simulation relation from S to itself. Then we generate a quotient system We remove irrational or redundant choices for the controller. Then we look on the environment side and remove its irrational transitions, and then remove the inaccessible states that remain. So step 0, computing the maximal alternating simulation relation, is a standard thing that can be done with fixed point iterations. ASRs are closed in their union, therefore we know there exists a maximal relation from S to itself that contains the maximal number of pairs of states. In this example, this is the relation that we obtain by running such an algorithm. Actually, the reflexive and transitive closure of this. So Q0, Q1, 1 is in the relation, but of course, all the reflexive entries are in the relation. And if these two are related and these two are related, then these two are also in the maximal relation. The intuition is that our max gives a hierarchy of states in terms of difficulty to control, irrespective of specification. So these two states have the same output, but in this state, the environment is more powerful than here. The same for the other entries. Now, the steps. Step 1 is generate the quotient system. This is a standard procedure, but it's not the quotient based on the output map. It's based on symmetric entries on the relation. So in this example, these two states are related to each other mutually. So we can quotient them together into a single state and then just place all the transitions that are into or out of them, obtaining this system. The new maximal alternating simulation relation from the quotient system to itself now has no non-trivial symmetric entries. It's a partial order. Now, this is a standard approach for reduction of systems. Our contribution starts really now. Step 2, we remove irrational control actions. What do I mean by that? Take any state and any two actions from the state A and B that are different. If for every transition that can be picked by using B, there exists a transition by using A, such that XA, XB is in the relation, that means that by using A, I can end up always in a harder to control state than an XB. Therefore, A is irrational for the controller. It's never good to choose this action from the controller perspective, or at least it's just redundant. This is the case of this transition. W and S are redundant from this state, so I can just pick whatever. I don't need the two transitions in each case. While here, W can pick if I pick W as a controller, the environment can pick this transition or this transition. It has more options than if I pick S. Therefore, it's better that the controller picks S in this case. So W is removed as well. So here we reap a few more transitions. Step 3, we remove irrational transitions. Now, looking from the environment perspective, we call PAQ prime a younger sibling of PAQ when QQ prime is in the relation, but Q prime Q is not. What does it mean? Is that if controller picks A, it's never good for the environment to choose this transition as opposed to this, because Q is better for the environment to counter control than Q prime. So I remove all of the younger siblings. This is the case for the initial transition, initial state here, which we assume without loss of generality to be picked by the environment. And this is also true by this transition S here that we remove, because I can either go to Q01, which is easier for the environment, or to Q11, which is harder for the environment. So this one is eliminated. Step 4, we remove inaccessible states, where we actually reap the most benefits, obtaining a very small system in this running example. Our main results, of course, there's the correctness results. We prove that every step preserves alternating simulation equivalence. And furthermore, if you consider a system that violates assumption Ni for any I from 1 to 4 among this list, N1, no distinct states PQ are equivalent, meaning they are symmetrically related in the maximal alternating simulation relation. N2, no state has irrational or redundant actions. N3, no transition or initial state has younger siblings. And finally, N4, every state is accessible from X0. If any of these conditions is violated, say N3, we apply step 3, and we can strictly reduce the size of the system while preserving ASC. Therefore, a lemma is that all Ni are necessary conditions for minimality. Now, we also prove that by applying step say 3 on a system that satisfies conditions N1 and N2, we still satisfy the former conditions and additionally satisfy the new one. So applying the steps in the right order guarantees that the obtained system satisfy all of these conditions. Then the most interesting lemma of our work is that if two systems satisfy all of these conditions and they are alternating simulation equivalents to each other, then they are isomorphic. This BABI isomorphism that I'm going to explain next. This implies that they have the same size, and therefore we obtain our final theorem is that our algorithm returns the unique up to BABI minimal system that is equivalent to the original one. What is BABI? It's the bijective alternating bisimulation isomorphism. It's an isomorphism on graphs up to a bijective renaming of labels per state. So these two graphs here, they are easily isomorphic modulo renaming of labels because I can just replace A's by bicycles, B's by cars, and C's by trains. And here I'm just flipping A and B, comparing these two. But this is the most interesting and most special about BABI. Here I can rename C by A. So they are globally, they are not really isomorphic, but per state they are. So for B, it doesn't matter if I call C or A, there's only one transition on one action that is going to itself, and that's it. So these systems are BABI to each other. This is instrumental for our proof of minimality. Now, we implemented this algorithm in a case study, which is scheduling of event-triggered controllers. I cannot explain in detail what event-triggered controllers are, but it's simply control systems where the sampling is dictated by some event based on the state, on the planned state. And the only way that exists so far to schedule these systems is by using finite abstractions that are pretty much the running example that I showed. They have this shape where states have output T if a plant has just transmitted its message to the controller, or W if it has just waited one time step. And then the scheduler can choose to sample or to wait. And in some situations, even if it waits, the trigger can happen and the transmission occurs, even if the scheduler doesn't want to. So this is the W here, bringing it back to T. The conflict-free scheduling problem is that we never want two T's at the same time if you have only one communication channel. So we want to avoid communication conflicts. We implemented our algorithm and we obtained reductions of up to 50 times in system size. So we got an abstraction of an ETC system that had 500 states and 2,000 transitions, and it was equivalent to a system with only 11 states and 21 transitions. And the scheduling problem in some cases, if we had 6 of these plans try to be scheduled simultaneously, we got a speed up from 15 minutes approximately to only milliseconds on solving the scheduling problem. And in some cases, the best 5-fold reduction in the scheduler BDD size. So this shows the practical relevance of this algorithm. And we can conclude the work. First, we propose a first solution to minimize a given finite system, preserving alternating simulation equivalence. And it's in fact a polynomial time algorithm. This is the smallest system that is unique modulo alternating simulation equivalence, up to a special type of isomorphism. We also show that using this algorithm can give massive time and space reductions for scheduler synthesis of multiple event-triggered control loops. For future work, we plan on extending this algorithm for infinite-state systems and weighted models, developing on-the-fly algorithms to improve space complexity, prove lower bound complexity for the minimization. We only have the upper bound now, and design some type of lazy abstractions based on a refined, minimized iteration. This concludes the talk. I hope you enjoyed it. I'm looking forward to your questions. Thank you very much.